I am actually not at UT Austin right now. I'm a software engineer in Houston, but I was a postdoc, Bing fellow at UT for about 3 years. And that stopped 2 years ago, but I'm still working on this problem. So here I am to talk about it. So this is
okay, Ryan, you change your major?
Yeah.
So right now you are you're a software engineering?
Yeah. So this is joint work with Natasha and Thomas. They're great mathematicians at UT Austin, good friends of mine. So basically, I'll introduce Boltzmann's equation, say a little bit about the streak arts estimates we're going to use, because it's going to be the sort of prime focus. Main result, which was actually published earlier this year in ARMA, and then some basically frontiers, some of which we're working on now, and references at the very end. Boltzmann's equation, what is it? So, well, okay, so what do we have on the left here? This is like a free transport, just a particle moves in a straight line, okay? So it's sort of the classical version of this linear Schrodinger equation. We include the time. What is this on the left? So basically you should think about like a gas. Say in relevant regime would be like, say, the upper atmosphere, where it's very, very dilute. So it's going to be these collisions between particles, and somehow energy is going to become more diffuse. And you look at the phase space coordinates, so you get your x and your v. So this is really an equation posed in phase space. And I put the picture of hard spheres here because I used to work with hard spheres only. I eventually realized that hard spheres were way too difficult. So now I work on easier problems. But the change of variables is the same. So basically, when you're doing a collision, you can exit your current little box of phase space, which is just proportional to f. So you get your minus here. And then you can gain, which the gain part comes from all possible scattering problems that can go into your current sort of line of sight. Wherever you're going, you look at all possible ways things should collide into that. So basically, you have to solve a scattering problem. Now,
Ryan, from Boltzmann equations, what equations what applications? So why people care about
why do we care? Well, one of the great things you can do with this that always fascinated me is it gives you a kind of semi-rigorous, sometimes rigorous way to think about hydrodynamic limits. You know, in probability theory, you have all kinds of different hydrodynamic limits where you take some like lattice model and then you rescale x and t, and you get some like, you know, conservation laws, you know, maybe Stokes or something. And you can do the same thing with Boltzmann, except with Boltzmann, you're using this actual physics because it enters through the scattering kernel, this function b here, whatever that b is. Because the b is actually comes from it's proportional to the cross section of whatever is coming from the physics, you know, your Landau and Lifshitz sort of problems. And so you compute the scattering cross section, and then I think you I don't remember if you multiply, I think you multiply by the relative velocity, and then you get b. So basically this b is just encapsulates all the physics of how the particles are colliding. But does that answer your question? I mean, I think the most important thing people try to deduce from Boltzmann equation would be hydrodynamic limits. So for example, you can derive Navier-Stokes equations from Boltzmann's equation. Same with Euler equations, things like that. So that's one of the big motivations for studying Boltzmann's equation.
Oh, I see. Okay. Thank you. Yeah, that answered my question. Yeah.
There are others. I mean, they're like a non-equilibrium phenomena in I think like involving like electrons propagating through a metal and things like that, where it's not where you don't rescale variables. But usually when people talk about Boltzmann's equation, they care a lot about hydrodynamic limits.
Okay.
Yeah. So always when we talk about Boltzmann's equation, we're going to have this sort of change of variables, which, you know, you can kind of deduce this one when you look at hard spheres, but it's always the same because this change of variables just comes from thinking about basically conservation of energy, well, kinetic energy and the momentum and the angular momentum. and you get this sort of change of variables, taking your incoming velocities, which are the V and the V star, into the outgoing pair, which is the V prime, the primed ones. So then that's going to come into your Boltzmann equation as the positive part, and then the negative part will come with a minus sign. So the minus, this sort of a very important decomposition, which for basically every physical interaction you can think of, you can't actually split Q into plus and minus because these would both individually be infinite. But for something like, say, a hard sphere model, or really anything where the interaction is very localized, you can actually justify this splitting where the Q plus and the Q minus are treated separately. And this is actually very important because all the work I talk about today relies on that decomposition into the plus and the minus. Okay. Let's move on to the math. So this free transport, the straight line propagation of a particle, actually, if you take the Wigner transform, which means basically you look at the sort of quantum analog of a classical system. And what you get is this hyperbolic linear Schrodinger equation. Gamma would be a density matrix, and then this bracket is a commutator. So in other words, this one on the top with the F is formally equivalent to the one on the bottom with the gamma. So this is interesting because if gamma was basically of a factorized form, an outer product of phi with itself, then this equation here with the commutator is equivalent to a linear Schrodinger equation for phi. But the analogy with classical physics then here breaks down, because if you do this sort of factorized version of gamma, then whatever phi you had, whatever F corresponded to that would not be everywhere non-negative unless your phi was a Gaussian. So we don't get a perfect correspondence between quantum physics and classical physics, but it is sort of an interesting analogy. So we recall the well-known Streekart's estimate. Since there are many experts here, I hope I didn't get this wrong. I double-checked the slide several times. But basically what it's saying is that if you take some L2 data, and everything I talk about today is in L2, then you can move by the free Schrodinger evolution, and what you get are some kind of boundedness of norms involving time and space, and sort of this numerology here with the Q's and the R's is somehow determined by the scaling of this equation in X and T. And then so the interesting thing is you can get the same kind of result for a kinetic equation. So instead of doing the e to the I t delta, you're doing e to the t v dot grad x. So it's the same, this equation, we just look at this linear propagator, but we are going to do, so that when you compute that evolution, it becomes x minus vt because it's a straight line. So then you do the same kind of game, and you have mixed integrabilities, but now it involves time and space and velocity, okay? And then you put in, we'll think that A here is equal to 2. So it's like F naught in L2, okay? So then all of the rest of this, these are, I mean, I gained some intuition about how these numbers relate, but for now, let's just call them exponents. So as far as how these sets of inequalities relate, at least away from the endpoints, those Streekart's estimates for Schrodinger are going to be equivalent to the ones for free transport. In other words, you can kind of get back and forth from one set to the other set. And just a word about how these kinds of estimates are proved. For kinetic streetcarts, we usually use what's called the dispersive estimate, which basically says if you look at the L1 and V, which is like the spatial density, then it has some kind of a soup norm bound as long as you take your data in a suitable functional space. And so this is a very important inequality. It's trivial to prove. It's basically some kind of change of variables using the fact that the X ranges over the whole space. And but you know, it's kind of an interesting fact that sometimes you can actually prove the Streekart's estimates, the one from the previous slide, without the dispersive estimate. And that is a remarkable paper by Delvin. Now, these streetcar estimates are used throughout kinetic theory, not so much for Boltzmann, but for other kinetic equations like Vlasov equations. Diogo Arsenio in 2011, in a very nice paper in CMP, used these streetcar estimates to find global small solutions of Boltzmann's equation with some non-physical collision kernels. And really, all the collision kernels in this talk are non-physical. But really, the reason I think that these types of techniques for Boltzmann haven't gotten that much attention is that when you look at these mixed norms, you're taking different integrabilities in time and velocity and space, and it's just really hard to manage those various indices and close an estimate for the whole equation. And there are some other reasons as well that we'll talk about maybe if we have time. So as I mentioned, we have these global solutions, small solutions for Boltzmann's equation using streetcars by Arsenio. But there was a limitation in his result, which that he could not take a collision kernel, which was like a power law in velocity. So all the ones from physics are some kind of power law. And the reason he couldn't do it, and sorry?
Yeah, so are you using the mixed norm, the streetcars equality all the time, or just using the symmetric streetcars equalities?
So to be clear, what we end up using are these homogeneous streetcars estimates, and actually what we use in the paper, you'll notice here the theorem gives you non-endpoints. A has to be less than Q. The one that we use in the paper formally is actually outside the range of this theorem. And in fact, the theorem is false for the one that we use, because the one that we use has A equals Q equals 2. And then P is 4 and R is 4/3. So you're really using the different integrabilities in time, space, and velocity. And the reason I say it's false is because the situation A equals 2 in this theorem is always false, and that's known. So the question becomes, why can we do this? And the reason is because if you go back up to here, you have this kind of equivalence between a classical equation and the quantum one. So this is basically comes from a Fourier transform in the velocity variable, which is this Wigner transform. And when you do that, the 4/3 in velocity becomes 4. So it's more like an L4 bound in two spatial coordinates, x and x prime. That's how the density matrices work in quantum mechanics. So, and that actually brings us into a regime where we can apply a result of Thiel and Tau, endpoint streetcars estimates, a very classical paper. Well, classical for this field, I guess. And so that basically was transforming a classical requirement into a quantum type requirement that allowed us to obtain the necessary bounds. But intuitively, it's something like these homogeneous streetcars estimates. Okay.
Yeah, so my concern is the Boltzmann equation and the Boltzmann equation, like the Euler equation, imply the Levi-Stokes equation, right?
So I should point out before we go there that even though Diogo did mention these hydrodynamic limits in his paper, the fact is that nothing in his paper and nothing in our paper, if you take the relevant scaling limits to those hydrodynamic limits, if you just look at how the scalings work out, our functional settings don't actually give you hydrodynamic limits. It's
so I know. So my
possible.
concern is we have very good nonlinear Schrödinger equation model so that we can apply the streetcars equalities, but it's very hard for us to imagine like reverse the process to make or apply the streetcars equalities onto the very original or very uncontrolled equations, you know, until we make some artificial assumptions. So I don't know. So continue, yeah.
Yeah, I mean, it's a good question. And in fact, even if you look at particle systems, you can start looking at whether there are streetcar estimates, and it turns out there are. And so even if you think about the derivation of, say, cubic NLS, so actually a quantum dynamics, there are techniques where you can use streetcars. And I think my own postdoctoral advisors worked on kind of these ways of extracting information about a particle system using streetcar estimates. It's very interesting work. Yeah, what you're saying is valid. It's very difficult when you're talking about correlations of particles to figure out a way to use dispersion, but it can be done.
Okay, yeah.
Okay, so basically this Q minus, the loss terms, let me remind you what the loss term is. So Q minus here is the loss term where it subtracts. And the reason that Diogo could not take a power law type here for B for any power was that if you look at this Q minus, it sort of multiplies against F. So if I just thought about Q minus, I could kind of pull one of these F's out here to the outside. So it's kind of like multiplication by F. That multiplication by F causes all kinds of problems because the best you could hope to do would be something like Holder, multiply two things together. If you look at the gain part over here, the Q plus, when you're doing F prime, F star prime, both of those two factors are coming through some sort of convolutive process, which is this scattering kernel, okay? It's going through a change of variables. So you never look at the sort of local tendency of F by itself. It always goes through this kind of convolutive structure. And it turns out that Q plus is well known in the kinetic theory community, has a lot of nice properties that Q minus doesn't have. For instance, for certain collision kernels, for certain nice collision kernels, the Q plus acting on F will actually be smoother than F itself. And that is not true at all for Q minus. Can't be true. So there are some compactifying properties that you get from Q plus. So because Q minus is somehow worse, Diogo was not able to handle these scale invariant collision kernels. That is still the case. There's no indication that that can be improved. But what we found was that if you change your choice of norm, if you somehow change a little bit, somehow keeping the problem scaling critical, but adding an auxiliary norm, then there was a way to basically deal with these power law collision kernels. And we just worked with the constant case because already with a constant collision kernel in 2 dimensions, the simplest Boltzmann equation you could ever think of, it turns out to be very difficult. So the relevant space, basically, if you think about a constant collision kernel in 2 dimensions, it so happens you can calculate that there is a full family of dilation symmetries separately in space and velocity, all of them preserving the space L2 in space and velocity. So that means you just take your F, square it, integrate in dx and dv with the standard Lebesgue measure and take the square root. So somehow this L2 has some direct relevance to that equation. If you took other collision kernels and other dimensions, this would not be the right functional setting. So then what we get is a kind of a small data global well-posedness with scattering. And we do need some kind of relative regularity and decay conditions on the data. But the key point here is that the smallness only comes for the scaling critical norm, which is L2. So that's why we can say it is a kind of a type of scaling critical result. So this is the theorem, which was published earlier this year. I think in February, ARMA. The collision kernel is 1, the dimension is 2, so we're just thinking in the plane. It's the whole plane. We can't do a torus. It has to be the whole plane because we use the dispersion. And what we're basically thinking is a situation where your data needs to have basically at least half a derivative. So this doesn't have to be bounded even. Your data doesn't have to be bounded. The spatial density doesn't have to be bounded at t equals 0. All that we ask is that number 1, that this half sort of bit more than half a derivative is with the corresponding decay and velocity is finite. And then we ask that the L2 norm of the data be small. So this is our scaling critical norm. L2. So then C is just an absolute constant. And then we get a unique global solution F. That solution again has this same regularity class for all time with the half derivative. And also we can show that it is scattering, which means that it's approximately a free flow at positive time. So there is some L2 function F infinity. I don't want to say it has half a derivative. I don't know actually if it does or if it doesn't. But at the very least, we can say that our nonlinear flow is going to be close to that one, that F infinity, the linear flow at large time. So that was our result. And I should also point out, since this is a harmonic analysis audience, that now if we just took alpha equals 1, the regularity arguments here with alpha equals 1 is fairly straightforward. You just use the regular, the usual calculus sort of games. When alpha is between a half and 1, which is maybe a bit more interesting because we have truly very unbounded behavior, not just like log unbounded, but actually unbounded. And that in order to deal with that, we actually had to use some old results by Koenig, Ponce and Vega, where they were treating, I think, KdV in one dimension. It's the relevant fractional estimates that they had can be extended to higher dimensions. So that's how we got the between a half and 1. And this critical 1/2 for the regularity, you can see it in other ways as well. You don't have to only see it in terms of their results. There are other ways to see how this 1/2 shows up. So the proof of this theorem comes from basically what we prove is some kind of it's kind of like what Bourgain was doing with his XSB spaces. The big difference is that instead of trying to quantify the time dependence on the Fourier side in time, we're actually using the usual just L1 side in time. And actually that's why we can get the scattering, because it's L1 in time. So then what we find is if you take some initial data and then or you could take 2 different initial data and we just push them through the free flow. So it's just a free propagator and we look at the action of Q plus on the free flow. And then we want to control whatever is going on in the same space on both sides. So you see, we don't even have like LPX, LQB or anything like that. It's L2 on the left and it's L2 on the right. But then the key is that you're not talking about L infinity in time. You're talking about L1 in time. And this won't be true unless you use the L1 in time. And so this estimate, actually, yeah, let me say yes. The proof of this estimate is where we use the endpoint streetcarts of Kiel and tau, and you can kind of see that because it's L2 and B, you may use the Fourier transform in velocity, which we do to take us to a Schrodinger equation where we can apply endpoint streetcarts of Kiel and tau. This estimate here with the Q plus, and again, this doesn't hold for Q minus, it has to be Q plus because it's Q plus where you get the convolution. With Q minus, you're multiplying against F, and that actually forbids this type of equation to hold because you're using Holder's inequality instead of Young's inequality. Q plus obeys some kind of Young type inequality, convolution inequality. This inequality, if you just take scalings, this set of scalings here with the lambda and the mu actually preserves solutions of Boltzmann's equation. So it has some kind of 2-parameter set of scaling symmetries. Lambda and mu are any positive real number. So if you take this scaling and you plug it into this Q plus bound here and you work it out carefully, you'll find that this bound again respects this same set of scaling symmetries. So basically, if you took this same equation, Boltzmann, and you just threw away the loss term, Q minus to 0, then we can solve in the Q plus only equation just in the space L2, using just the bound that I showed you at the end. The question becomes, and why we had to use the regularity and the half derivative and everything else, was to handle this Q minus. And and again, to handle the Q minus, basically it's a very technical procedure. I think the paper is like 50 pages long or something, 40 or 50 pages long, just to deal with this loss term. And if anyone knows about kinetic theory, they'll know about these two things. If not, then they won't. But we use this Keneal-Shinbaugh iteration, which is classical in kinetic theory, and velocity averaging, which is another classical technique in kinetic theory, and we can get the well-posedness. Okay, so what I told about was small data global. You can talk again about local well-posedness for any size of data. It is possible. You have to make very many modifications to the proof. It's not straightforward. And even to define the time scale, because we saw that there was some kind of higher derivatives and subcritical norms sitting around, and that would still have to be finite. So then you say, okay, what does it mean to have the time of existence be only about L2? So you have to define what is the relevant time scale for the existence. And it isn't just depending on the L2 norm, because it's a critical problem. So you can't just use the L2 norm. So you have to somehow carefully think about where the time of existence for a local solution comes from. So I'm not going to explain exactly where this time of existence comes from, but it is actually an L2 type local existence. And you need some kind of auxiliary norm. And finally, since it's partial differential equations, we like to talk about large solutions or blow up, or just figure out which of the two is happening, whether you have global solutions or blow up. For this particular equation, honestly, not too much is known. It's very difficult because the space where the conservation laws happen is something like L1 or L log L, which is well below L2, which L2, as we saw, is going to be the scaling critical space for this equation. And honestly, if you look at other Boltzmann equations, higher dimensions or other collision kernels, it's going to be worse than L2. So this is like our best case scenario. The easiest possible case is what we've been talking about in this talk, of a constant collision kernel in 2 dimensions. And already we are so far from the conserved quantities that there's little hope of saying anything about global. Okay, so these are our papers. We got the Kiel Tau, some influential works by Erdős and Yao, important work by Kleinerman and Macedon, which was kind of the inspiration for everything that followed. And thank you so much to the organizers and Professor Shao for the opportunity to speak.